Good evening, everyone, and welcome to the Amateur Radio General Class, session number 4. During our previous session, we had our usual Q&A. We had a look at the reminder for persons who had not yet completed or taken the technician class or needed a review. We had a look at where we are in the curriculum. Also mentioned the practice exams that we encourage participants to take even all now at early days in the course. Also mentioned Zello as an opportunity to interact with React as well. And we had a quick look again at the general class course material as well as the optional material that students can acquire. We then summarized the electrical concepts that we had covered so that we have a relative view of some of the topics and the formulae related to the various electrical concepts. Then we introduced Kirchhoff's current law. We went into alternating current or AC values such as peak, peak to peak, root mean squared or RMS, and we did some worked examples. We also then discussed the power formula for both AC and DC circuits, and we did some worked examples. And then we ended with peak envelope power, or PEP, PEP, and we did worked examples also. Then followed by our usual question pool review for all of the questions in the question pool that related to the theory that we would have covered. And of course, we set the next session. Okay, so agenda for this evening. So again, we'll remind persons about the technician class material. We will have another look at where we are in the curriculum. We'll mention the practice exams again. Persons are still asking about Zello, so we have that slide that we'll probably run for a little bit again. We also have the slides up again on the general class course material and optional material. We keep getting questions from participants, so we'll repeat that for as long as necessary. Then we get into our question and answer, as well as we begin the technical topics for this evening. So again, this being the level 2 class, which is the general class, we'll do a quick review of logarithms because we'll need that when we discuss decibels next. So decibels or dB in relation to power, and we'll do worked examples. Then we'll talk about resistors that are connected in series as well as parallel and do some worked examples, calculations. Then we deal with other components called inductors, also connected in series as well as parallel with worked examples. And then we end off with capacitors, also series and in parallel with worked examples. And we'll just quickly recap, what are resistors, inductors, and capacitors in case there's anyone who has not yet covered these topics in the technician class. And we are highly encouraging persons. By now, this is week number 4. So there's been quite an ample amount of time to begin reviewing the technician class. We know people are busy, but it will help understand the material a lot better if you were to cover the videos in the technician class. But we will take into account that not everyone has had a chance to look at it in detail yet, and we will quickly recap some of the concepts very early. All right. So again, persons are asking about the slides, where you can get the slides for the sessions as well as the handouts. Folks, this is the link, tdocs.ttreact.com. That's where you'll be able to see all of the PDF slides themselves. And for all of the recordings, it's available on this playlist, tvids.ttreact.com. So this is for this part. Sorry, I should say this is for the technician class course, right? I have another slide up that shows the links for the general class that we are presently doing. So for the technician class course, these are the links that you can access all of the material, all of the slides, all of the handouts, as well as the playlist for all 16 sessions of the technician class, right? So we'll continue to repeat this slide because we keep getting questions, how do I get the technician class material still? So we'll run these slides for the next few sessions. for persons who may need to catch up. All right. So again, these are the various topics that we have to cover in this course, and we are in early days yet. We're the first topic, electrical principles, right? Okay. So we are also advising persons in the course, participants, please consider taking the practice exams, because these practice exams are taken from the same question pool that are used in the real exams. So when you take these practice exams, it gives you an idea of where you are with respect to your knowledge of the material. And it should also garner your confidence as you continue repeating practice exams as the course goes along. So we highly recommend, don't wait until the end and then to now start taking the practice exams. Many students often find that they're quite surprised as to how well they do, even within the first couple of weeks, because of prior knowledge and reading ahead and all that sort of thing, right? So highly recommended to consider taking the practice exams. Of course, there are several links. Some of these links may come and go. So we have a few of them that's recommended for you to look at. Again, persons keep asking about Zello and the nets. So we have had a few persons in the course join the React members channel on Zello. So it's up there on your screen. You have instructions there. Simply download, install, create an account for yourself, and then you want to join the existing channel called React Members. React with a space and members. Pretty active channel, lots of information, especially in respect of weather and other happenings there, and all are welcome to participate on the channel. You can initially listen for a bit, but certainly a lot of information there, and it can also help you practice your radio operating procedures. Because on the channel, while Zello, it's a free app, no licenses required, because the channel is used for React operations, we do insist on proper radio operating practices. So don't worry too much if you're not that familiar. The channel tends to be a bit kind to newcomers, and we will help you. We will certainly advise, and just observing a little bit will give you an idea of the protocol involved. And we will also, a little bit later in the course, be sharing a video that you may wish to look at on practical radio operating tips that can help you in your operations. In the amateur radio course, we focus on all of the material for the syllabus, but there's a lot more besides that, about becoming a radio operator and an amateur radio operator as well. So, okay. So coming to the material for this course that we're in, the level 2, which is the general class course. So these are the links on your screen here where you can get access to all of the material for the current course. So gdocs.ttreact.com is where you can get all of the slides. This slide deck that we're showing on your screen, we circulate that via this link. After every course, we place those slides inside of there. So as we progress on, you will see that repository building up as we go. And there's some other documents, such as what you're seeing on your screen here, the actual question pool, part 97, and another good reference document that are all shared as PDFs inside of this link. So please become familiar with this link. Persons keep asking, can you send me the slides? Now, we have avoided sending slides because these are between 5 and 8 megs per slide, right? Pack. So that can fill up persons' email inboxes quite quickly. So we have opted to just put them in this repository and circulate the link. So you need to go to this link and you will see all of the files inside of there. Again, we'll repeat this a couple times again over the next few weeks. Persons are still unsure where to get information, and we want to be as helpful as possible. So also in terms of the videos, again, we do send the link out after each session, and there's a repository, gvids.ttreact.com. If you go to this link, you will have access to all of the videos that would have been recorded thus far for this level, right? So this is the general class course material. What we shared a little earlier, a couple of slides back, will be for the previous course, the technician class. So very similar links. So bear in mind, this is for the current course. All right. So again, optional material. These are the recommended texts that you can decide if you wish to purchase online to your favorite site, such as the Amazon website, amazon.com, or the author's website. So we're using this book called The No Nonsense General Class License Study Guide, and the author has a link so, that you can purchase a PDF copy of the book should you choose. Again, it's optional, not required at all. However, it's highly recommended that you acquire at least one manual for your safekeeping, and also to support the authors as well. They spend a lot of time and effort preparing their texts. So given that we're using it, please consider supporting the author and purchasing the books. They are quite relatively reasonable. So if you can afford it, please consider supporting them, right? Again, not required though. There's no obligation whatsoever for you to purchase anything. Okay. Right, so let's go into the Q&A. So the first question is, where does the value of 0.707 come from in the RMS formula that we dealt with? So remember we said if you have a peak value and you want to figure out the RMS, you just simply multiply by 0.707, right? So this 0.707 actually, when you work it out, it's 1 over this square root of root 2, right? So if you look on your screen here, 1 over the square root of root 2, that is where the 0.707 comes from, also the 1.414. So just to give you an idea. So that's why we say it's a reciprocal of the square root of 2, and it is a value that is used to convert from peak values to RMS values. So if you were to look on your screen, you will see the sinusoidal wave or the sine wave of an AC signal, right? So AC current, for example, right? So there's a increase in the voltage, it goes to 0, decrease to trough, and then goes back up to 0, right? So this is one wave or one cycle, right? And you can see this is the peak here, and this is the RMS line. So if you want to get the RMS value, you multiply it by 0.707, and that's how you get the RMS value, right? So hopefully that's helpful. So again, we did deal with this, but a question is, well, why do you use RMS values instead of peak values for AC voltages? So for example, in Trinidad and Tobago, we will say you have a 120 volt supply. That's 120 volt RMS. But the peak of that voltage supply is 169.7 volts peak, right? But we don't say we have a 169.7 or 170 volt supply. We say it's a 120 volt supply. And that is because we are using the RMS value. And why RMS? Is because it allows us to do a sensible comparison between an AC voltage and direct current supply, right? So the equivalent of it. The heating value, if you want to call it that as well, the equivalent heating value. Because this varies and peaks and troughs and so on, it will not be consistent in its heating, but DC is consistent. So you want to know, well, given the variation of this current, what is the equivalent steady state condition, right? So hopefully that helps a little bit. And then the last question, again, when given current and voltage for an AC circuit to find power, does one assume the current is RMS? IRMS, yes? And the answer is yes. So once it's AC, we use RMS, right? So it's often not stated in some formulae, but we like to make it explicit. So that's why we'll see IRMS or V2 or V squared RMS or VRMS squared, really. Right, so it indicates that the V, and you have the subscript as RMS. So it is V for voltage, and it's squaring, but it's the RMS voltage. So that's why we put it here in a subscript to show that the current is RMS current and the voltage is RMS current. So sometimes we leave it out, but we just need to know for our purposes here that it's RMS values indeed, right? So hopefully that little Q&A helps concretize some of the concepts, right? So you need to look this over, write it out, write it on a piece of paper, and become familiar with it, right? Writing does help, right? It helps learning. All right. So we're now coming into some of the new material for this evening, right? And before we get into the real topic, which is the decibel or decibels, dealing with decibels, we're just reminding persons of the concept of logarithms. Now, I wouldn't spend a lot of time in this because we covered this quite extensively in the technician class course, session number 4, actually. However, we repeated a couple slides so that we can make a link. What is logarithms, right? So please do take a look at session number 4. If you're not familiar, we did try a simple treatment on what logs are. And but we have just repeated a couple of these slides here. So just look it over in the technician class material session number 4. Have a look at those videos, right? So this explains what logs are, right? And we have an example here, and we'll just go through this for a moment. So we do need to be familiar with the exponent or exponential notation. So if you have the number 10 and you have the 2 in superscript next to the 10, what this means is 10 to the power of 2 or 10 raised to the power of 2. Another way of saying it is 10 squared, which actually means 10 multiplied by itself, which is 10 by 10. So 10 by 10 naturally is 100. So that's the notation here in exponent form, right? 10 squared is equal to 100, or 10 to the power of 2 is 100. But we can also reverse how this appears by using the logarithm representation of this exponent, right? And we did it in such a way so that you could hopefully realize that these two are equivalent and you can move from one to the next by moving things around. And you'll see why that is important when we deal with decibels. So we just try to give an explanation as to, how do we come up with those answers when we have a question, right? So this is important to note. Notice the 100 here is the number. Notice we put the number here. And we're taking the logarithm of 100, but to base 10. Where does this 10 come from? Well, this is the base right here. And the power is 2. In this case, this notation exponent is 2, it's squared. But when we take the log using base 10 of the number 100, we get 2 as the logarithm. So hopefully this helps show the relationship between exponent notation and logarithmic notation between the numbers. These are equivalent, right? So you notice the same values. See the 10 here, look at the 10 here. See the 2 here, you have the 2 here, and you have the 100 and the 100 here. All we have added is the log or logarithm notation. Notice that we can do log to other bases as well, but we are dealing with base 10, the decimal system. So hopefully that helps a little bit so that when we come into decibels now, it wouldn't be, too confusing for us, right? Okay, so what is the decibel? Again, we covered this in the technician class quite a bit, but we do need to repeat it a little bit here for the general class because we are introducing a little bit of we're going a little further with the information. So on your screen, you will see a radio, a transceiver, right, with a microphone. As a ham radio operator, you'll be using a transceiver to speak into the radio and someone will be hearing you on the other end. So you have the radio, and the radio will transmit a signal that will go out to the antenna. But sometimes this radio maybe is a low power radio and we want to improve or increase the power level. So we'll use something like an amplifier. So this radio, let's say, for example, will output 1 watt of power. And we're keeping numbers simple and small just for calculation purposes, right? So this radio, let's say it outputs 1 power. I can pass it through an amplifier to get 2 watts out. And that goes to the antenna. So what that means, we have a stronger signal that will leave the antenna, and therefore our signal will travel further, right? Or we'll sound clearer to persons that are further away, right? We may be trying to hit a repeater, or we may be trying to reach a person on simplex that is further away from us. So we use an amplifier. But notice, we have 1 watt leaving our radio, so you have 1 watt entering the amplifier. But we're saying that this amplifier boosts the power output to 2 watts. So a couple of things we will immediately notice when we do that is 1 watt in and 2 watts out. What is that? Well, it's an increase by 1 watt, but it's also doubling of the 1 watt to 2 watts. We are twice times. Now, in radio speak, we tend to not only talk about, well, we have got 1 watt in and 2 watts out. We talk about the relative power output, how many times that is, and we tend to use the notation, the decibel notation. And one of the reasons is that because large numbers or large increases in power will have a smaller digit value in terms of decibel. So you'll see that. Now, a 1 watt in, 2 watts out is doubling. But that is a 3 dB gain. And you'll see how we get that 3 dB gain shortly as we work out the formula. You could just memorize it. When you double the output power, that's a 3 dB gain. It doesn't matter what the input power is or the output power, as long as it's doubling, that will always be a 3 dB gain. So it could have been 10 watts in and 20 watts out. It will still be 3 dB gain because it's a relative power, a ratio of it. And no matter what the values are, it's always a ratio. And that's how we use the decibel to express whether it's a reduction or an increase, relatively, it's a ratio of how many times more or less, or higher or lower. All right, so we're putting up on the top of the screen here the decibel formula, and we're repeating it for a couple of slides. So you'll see dB is equal to 10 multiplied by the log to base 10 of the second power or the output power over the input power. That's what this formula is here. Again, we introduced that at the technician class level, right? So this is our formula here, our trusty decibel formula or power formula, right? So we did see that when we doubled the power level, as we did earlier, from 1 watt to 2 watts, we said that's a 3 dB gain. But how do we know that? Let's work it out. So here's a question, and it's actually a question in the exam, right? So we sort of killing two birds with one stone, so to speak. Right, so let's deal with the question. What dB change represents a factor of 2 increase times 2 or decrease in power? So what we will do, we'll split this question into two and deal with the case of increase first, and then we'll do on another slide the case of the decrease, right? So it's the same question, but let's look at it from the increase perspective first, and then we'll see for the decrease how it looks. So if it is that we are wanting to check, what is the dB change if we double the power? So let's use a value as we did in the previous slide. Let's say that our input power is 1 watt. So we started off with 1 watt and we want to double the power. So simple maths, 2 times 1 is 2. So twice the amount of power is 2 watts. So we are moving from an input power of 1 watt, as we saw on the slide before, right? So input power of 1 watt to an output power of 2 watts. So P1, which is the input power, is 1 watt, and P2 is the output power of 2 watts. So we are simply double the power, and we apply our dB formula. So we write it down. So that's the first step we do. In doing calculations, we write down the formula that we're going to use. And this is our dB formula, our trusty dB formula. So dB is equal to 10 multiplied by the log to base 10 of P2 over P1. So again, we have some little issues here with the formatting, right? This should be a subscript 10 and not the same level. So we apologize for that. That seems to be happening on PowerPoint from time to time, right? But the formula is better shown up here, right? Just note that when you have 10 log to base 10 P2 over P1, it's 10 multiplied by the logarithm to base 10 of P2 over P1, right? So that's why we insert the X or the multiply sign here for emphasis, right? So we write down the trusty formula first of all, right? And then we look to plug in the values. So we have said input power is P1 is 1 watt. So P1 will be 1 watt. That's the denominator. And the numerator is P2, which is the output power. So that is how the ratio is, output power over input power. So P2 is 2 watts. We have defined it here. So we substitute 1 watt for P1 and we substitute 2 watts for P2, and then we come down to this next row here. So we go to the next equation. So dB is equal to 10 as above, multiplied by the log to base 10 of P2 over P1, but we have substitute the values of P1 and P2. So we get 2 over 1, right? So if we were to do a quick calculation, 2 over 1 is actually 2, right? So it's actually log of the number 2. So in your calculator, when you go to the next step, what you'll be doing is taking the number 2 and pressing log to base 10. Not ln, and ln is natural log, so you're looking for regular log, log, right? So we drop to the next equation. dB is equal to 10, the same 10 from above, but we have now gotten 0.301. How did we get 0.301? We punched 2 into the calculator and then we press the log button, right, which is the regular log, a log to base 10, and that will spit out for us 0.301. So that's how we got from this equation to this equation. We took the log of the number 2 because 2 over 1 is equal to 2. And when we multiply 10 by 0.301, we get approximately 3. So we can see here in the case of an increase, twice times increase, that represents a 3 dB gain or a 3 dB increase. But let's do the same question now, but work the decrease and see what number we'll get here. All right, so what we are doing now is reducing the power by half, right? So we're starting out with a simple number of 2 watts, right? And then we're halving that to 1 watt. So That's a power decrease. So the input power is 2 watts, but we are now attenuating that signal. We are reducing the signal to 1 watt. So that's a loss, right? We're starting off with 2 and we're ending up with 1. So that's certainly a decrease. That is certainly a loss. Let's see what happens when we use our trusty formula and plug those values for P1 and P2. P1, remember, is the input power. P2 is the output power. So the input power is 2 watts. The output power is 1 watt. So we're halving the power, right? So let's see what happens. What does the dB work out to? So again, we see the same trusty formula. dB is equal to 10 multiplied by log to base 10 of P2 over P1. So we substitute for P2. Remember what P2 is? P2 is 1 watt because that's the output power. P1 is 2 watts because that's the input power. We substitute, so we get P2 is equal to 1 and P1 is equal to 2. So we get a half, or 1 over 2, or 0.5. So to get to the next row in the equation, dB is equal to 10 multiplied by, now how did we get negative 0.301 or minus 0.301? Well, we simply took the log to base 10 of a half, or 0.5. So in our calculator, we either divide 1 by 2, which will give us 0.5, or we just know it natively and we put 0.5 into the calculator. And then we press our log button. That will spit out for us minus or negative 0.301. You might be seeing a little pattern here. So when we multiply that out, it is approximately 3, right? So we just the nearest whole number or no decimal places. So you may have noticed from previously, when we increased the power by twice, we got a decibel gain of 3 dB. But when we decreased it by a half, it's minus 3 dB. So that is a pattern you should recognize there, right? So twice times power, it's 3 dB positive, and half times power, it's also 3 dB but negative. So the answer to this question for the exam, when they ask what dB change represents a factor of 2 increase or decrease in power, the answer will be 3, right? It's for increase, it's 3 positive, and for decrease, it's negative 3, right? So we're just showing how we work the formula, and you can just learn the answer, but hopefully it's helpful us to understand how we have derived the answer, right? So this something you may want to take a piece of paper, write the formula down as we have stated it here, and work this out and do this a couple of times so that you get comfortable. How did we go from here to here to here to arrive at this number? To develop a bit of an understanding. Again, not absolutely required, but again, we do light touch theory, but exam focus. So hopefully this is helpful to participants. All right, let's do another couple of slides before we take our break. So we want to do a worked example using decibels in relation to power, right? So this is an actual exam question also, right? So the question is, what percentage of power loss would result from a loss of 1 dB? So in other words, we say we have an input power of some value and we had a 1 dB loss. So the question is, in terms of a percentage, what will that represent from, no matter what the power is, it's a 1 dB loss, what percentage have we lost? That is essentially the question that they're asking when we dissect it. So we are going to use the formula that we are aware of and do some substitution and plug in some values and see if we can get a pattern and see if we could derive what that answer is, right? So let's go through step by step, right? So we have broken it down here. So we're using the same trusty formula as above here, right? So again, dB is equal to 10 multiply the log to base 10 of P2 over P1, right? P2 divided by P1, we take the log of that to base 10 and we multiply it by 10. That's the formula here. So we write it down again here. We have just added the X to show its multiplication here, right? So dB is equal to 10 multiplied by log to base 10 of P2 over P1, right? So let us start to substitute some of the values. So we're saying that we have a loss of 1 dB. So we know that's minus 1 dB. So we have stuck that in as the answer. So we know minus 1 dB is equal to 10 multiplied by the log to base 10 of P2 over P1. So that is the ratio that we're looking at. What is that ratio? What will the amount of power that we left? So we then now do some algebraic manipulation, right? So this is where a bit of the math comes in. Try to follow, not absolutely necessary, but we're hoping that persons can follow. We do algebraic manipulation here. So what we do to get from this row to this row is we simply move this 10 or transpose this 10. that's on the right-hand side of the equation here, and we move it to the left-hand side of the equation. So to do that, we have two ways. We can either shift it down to the bottom here, it's on the top here. So we shift it down to the bottom, or we can cross multiply, or we can divide by 10. Either of those three terms, if you're familiar with, will work. So some people are familiar with it. Let's just shift it down here, right? Which is what we have done. We have moved the 10 from here to below here. Notice it's disappeared from here and it's now below. Another way is we can divide both sides by 10. If we divide this side by 10, we get minus 1 dB over 10. And if we divide this side by 10, 10 over 10 is equal to 1. So that 1 is assumed here. So however you do your algebra, that is what we're trying to go from this equation to this equation. So once you follow either of those methods, cross multiplication or division or just moving or transposition, whichever you have learned or you're familiar with, either will work for you. However you have learned it, that's fine. So you're just moving this 10 below here. And that's how we get minus 1 over 10, right? Is equal to what remains, which is log to base 10 P2 over P1, right? So there we have it. Now, for us to come from this equation to this equation requires knowledge of logarithms. So that's why previous slide we showed you this, b to the base number to the power of L is equal to y, and therefore log to base b of y is equal to L. So we're going to use this relationship here to do some manipulation, right? So we're just rewriting this into an alternative form. So what we have done really here is manipulated where P2 over P1, we move it equals to, so this is what we're trying to solve for. We're trying to solve for P2 if we got P1, right? What is that ratio of the power, or what the percentage is? So we have it ready-made here for us, and we simply manipulate. So the base is base 10. That's how we get 10 here, base 10. Base 10 to the power of, but the power of what? It's to the power of this. So it's looking a little bit cryptic here, but it's 10 to the power of what this is here, right? Which is minus 1 over 10 dB. So it looks a little bit cryptic here, but this is minus 1 over 10 dB. So it's 10 to the power of minus 1 over 10 dB, right? So no matter how it looks here, that is what it is. So it's actually a little simpler than it might initially appear, right? So that's why I encourage students, write this out. Take a piece of paper, and if you're familiar with exponential notation, this is the exponent here. It's minus 1 over 10 dB is the power that you're raising 10 to. So hopefully we have put this in here to show this is how we transform from this equation to this equation using this relationship or knowledge of logarithms, that these two are equivalent. We have just written them or rewritten them in a different form. So we take advantage of that relationship to find out what this ratio is. And it's very handy. So we end up with, when we, of course, 10 divided by 10, right? We end up with 10 to the power of minus 1, right? So, minus 1 divided by 10 is 0.1. So we end up by 10 to the power of minus 0.1. So we solve for this. We divide this out. 1 or minus 1 or negative 1 divided by 10 is 0.1 or negative 0.1. So it's same 10 to the power of this. But 10, we simplify it, it's to the power of minus 0.1. So P2 over P1 is equal to 10 to the power of minus 0.1. But when we use this in our calculator and we punch in 10 and we do xy, x to the power of y, and we put the power as 0.1 or minus 0.1, it works out to 0.794 if you use a calculator. Now 0.794 in terms of percentages is 79.4. How did we get that? We multiply this by 100, right? So that's the power that's remaining. But we want to know, what is the power loss? So if this 79.4% is the power that you remain with after you have a loss of 1 dB, how much power do you have lost? So if our initial power was 100%, and the remaining power after the loss, or after the 1 dB loss, was 79.94%, then what is remaining? Well, we simply put 100 and minus the power that's remaining to get what the loss is. So 100% minus 79.4% is 20.6%, which is the answer. So what percentage of power loss would result from a 1 dB? Well, the answer is 20.6%, and that's the answer. So folks, we encourage you to write this out on a piece of paper, copy it initially, and then try to do it on your own by resolving it in your own mind stepwise, and hopefully you'll be able to come up with the same answer. So hopefully this isn't too bad. Hopefully it's at least stepwise it makes sense. Just meditate on a little bit, write it out, and hopefully, again, you do not need to learn all of this for the exam. You can just learn that for 1 dB loss, you have a 20.6% loss. But hopefully you would have understood that there's a stepwise process. How do you calculate it? It's not just a number, and that's why we try in the course to go a little bit of light touch on the theory, so you can see how these things are arrived at, and not just, 1 dB is 20.6% loss and you take it for granted. There's a process of how it's arrived at. So folks, now is a good time to take a little break, a 2-minute break. Take a stretch, grab some water, maybe a bathroom break, and we'll be back in 2 minutes time to continue the rest of our theory. Okay. Good evening, Adish. Great to have you there, man. All right. So folks, so we know it's a bit of algebra, a bit of maths inside of there. And, again, it's not necessary to learn this derivation, but hopefully, as you have followed the process a little bit, you can see that there are steps how we get the answer, right? So we do highly encourage, if you have the time, put it to paper, and the formatting as you write it out will be a little bit better, as on the screen there, right? Matter of fact, I was myself tempted to write it and take a screenshot of it, so it'll look a little bit more realistic in terms of the equations, right? There are some little limitations in PowerPoint there, right? A little bit of a challenge, a little bug as well that seems to be, no matter when we put subscripts, it's every now and again it reverts. Not quite sure why. So I do apologize for that, right? So we've done our best to write the notation as best as we can. So write it yourself and get familiar with some of the notations, and it will start to grow on you, hopefully. All right, so let's continue, folks, right? So again, we may need to go a little bit over time this evening just to cover the material, and especially as we are bringing back some of the technician class material to make a connection to the students who may not have completed much of those sessions as yet, right? All right, so just a reminder, the fact that we are using a water circuit analogy, right, when we talk about electricity, right, where in the case of an electric circuit or schematic, it's current that flows, the electrons that flows, and in the case of a water circuit, that current is water that is flowing, right? Just keep that in the back of our mind anytime we are talking about calculations and circuits. Think of what is flowing in there, think what is flowing, and maybe that will help us. That analogy will help us a little bit come to terms with the electronics that we're dealing with. All right. So in the technician class, we covered what resistors are. So just showing the slide, we won't spend any time on it. This is a symbol for resistor. This is what the component might look like. And this is what also other resistor formats may look like, right? So we're dealing with resistors in a circuit. And when we connect resistors in a circuit, so we have a schematic diagram on screen. And notice we have a couple of resistors back to back, daisy chained, one into the next. When we connect resistors like this, one into the next, this is called series connection. And we'll come and compare and contrast just now to parallel. So we would have dealt with some of this, but we'll reinforce it. Now, the question becomes, when we have resistors, each resistor will have a value. Remember, we had said previously that resistance is given in ohms. And one resistor may have a value of 10 ohms, may have 50 ohms, 100 ohms, 1 kilo ohm, and so on. And when we connect individual resistors, what is the effective resistance of all of them together? So if we connect them like this, the total resistance is a simple summation of the individual resistances. So if this is 10 and this is 10, we simply add 10 plus 10. Whatever this value is, we add it. Let's say it's 20. We get 10 plus 10, that's 20 plus 20 is 40. And if this is another 50, you get the picture. We sum or we add the values if the resistors are connected in series like this. So these are series connected resistors. And in terms of a formula, we'll write it as R total is equal to R1 plus R2 plus R3 and so on for how many of the resistors we have in this string or series. We do a quick worked example. Question is, if we have three resistors in series like this, and someone told us that they're equal values, and the total of them is 450 ohms. So those amongst us that are quick to say, well, if it's 450 ohms total and they're all equal, then each one must be 150 ohms. Some people would have worked that out mentally because this is 150, this is 150, this is 150. When you add that up, 150 plus 150 is 300, 300 plus 150 is 450. So this could be easily done in mental maths if you're able, but we can also write it out in terms of the formula R total is equal to R1 plus R2 plus R3. But we're saying that one resistor is equal to the other, right? It's equivalent resistances, right? So therefore the total R is 3 times R. And therefore, if we wanted to find out the value of one of them, it's the total divided by 3, right? Using this extrapolation of the formula here. So it may be obvious from just looking at it. This is just re-emphasizing that once you have resistors in series, you simply add them up to get the total resistance, right? So this is not an exam question, but it's just there for your information on series connected resistor, just a question. All right, so we now come to the other way of connecting components and resistors in particular here in parallel. So notice, whereas before, this is how we'll connect resistors in series, daisy chained, strung one into the next. So whatever current flows through one will have to go through the other and so on. There's no splitting of the current. It's going through daisy chain one to the next, right? But in this case here, notice that the current will branch out into the various resistors. It will not go through one and then the other and then the other. It will go and split, right? So these are called parallel connected resistors, this format here. And you could have 2 in parallel, 3 in parallel, 4 in parallel, 10 in parallel. You can have many parallel resistors. The issue is, whereas before in series, when we added resistors in series, we summed or we added the total resistance to get the, for each one, we added them up. But in a parallel circuit, while you, in the case of the series resistor, we have an increased total resistance when we added more resistors. In the case of a parallel, the more resistance you add, you're actually lowering the resistance, right? So that's the property of a parallel type circuit with resistors. And we have a formula that the R total is equal to 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So the more resistors you have, that is why the total resistance becomes less, the more resistors that you put in parallel, right? So this is the formula here. And there's a case where if all of the resistors have the same value, you could simplify the formula by saying one of the resistors over the total number of resistors. So if it's 6 resistors, this number in the denominator will be 6. If it's 3 resistors, this number will be 3. All right, so 2 formulas, this is the quick formula here. If it happens to be all the resistors of the same value. If they are not of the same value, you have to use this formula, right? So notice the reciprocal, 1 over, and then 1 over and 1 over and so on, right? So notice this formula here. All right. So let's do an actual worked example, and this is a question in your exam. So on the right-hand side here, we have attempted to show what the diagram would look like for the question, right? So let's get straight to it. What is the approximate total resistance of a 100 and a 200 ohm resistor in parallel? Let's dissect this question. What are they asking us? The total resistance. So therefore, we know the answer is going to be in ohms. It's going to be some total resistance. But total resistance of what? Well, 2 resistors. But how are they connected? Are they in series or parallel? Well, they told us it's parallel. So we could draw a little trusty diagram and show we have 2 resistors in parallel, R1 and R2. But did they give us values of R1 and R2? Yes, they did. The first one is 100 ohm. That's R1. The second one is 200 ohms. So that's R2. But they are in parallel. So we have to use our parallel formula. We cannot just simply add 100 to 200 and say it's 300. No, that would be if they were in series. We have to use this reciprocal format of the formula. And, well, let's use this one. I mean, there's a simplified version as well, but let's get with this structure. So the total resistance is 1 over R1 plus 1 over R2, right? So 1 all over this. So let's substitute for R1 and R2. So we're using this as our base formula. And we substitute 100 for R1 and 200 for R2. That's all we're doing. We're substituting these 2 values that we got, that they gave us in the question. When we solve, we notice 1 over 100 is 0.01. 1 over 200 is 0.05. So we end up with the next equation, R is equal to 1 all over 0.01 plus 0.05. 0.01 plus 0.005 is 0.015. So that's how we have R is equal to 1 over this. So we've kind of taken you step by step, the substitution and the calculation, so you can see how we're getting from each step to each step, right? And when we use our calculator and divide this, 1 divided by 0.015, check me on this, use your own calculator, work this out, you should get approximately 67 ohms, which is the answer to this question. So you can learn the answer, or you could learn how to calculate it in the exam, and you permitted a regular non-storage formula type calculator in the exam, and you can, if you know this formula, you can work it out. So you don't have to remember the answer, right? Because you are using the formula. So first thing we do, draw the diagram, show it's in parallel, and then write in the resistors. I will even put in the values here on the diagram as well. Use our formula, and we work through stepwise. All right, let's do another one, a similar question, but in this case, we have 3 resistors instead of 2. So the first case, we had 2 resistors, we worked out the value. They're now giving us 3 resistors, similar question. Let's deal with it. This is an exam question. Remember the little tip we have given? Most of the time when we have a slide that have the text is in this yellow, these are actual exam questions, right? Or content from your exam. what is the total resistance of a 10, a 20, and a 50 ohm resistor connected in parallel? All right, let's dissect this question. What are they asking us? They're asking us to calculate the total resistance. So we automatically know, all right, total resistance. So the answer is going to be something ohms, right? Because resistance is given in ohms. And of what? Well, it's resistors. How many of them? They have given us 3 resistors. The first value, R1 is 10, R2 is 20, and R3 is 50. So we draw a little trusty diagram here to show 3 resistors in parallel, not series. They told us it's parallel, so we have to draw them like this, current splits. And we'll put the value here as well. R1 is 10, R2 is 20. We write them in, right? R3 is 50 ohms. So we have our 3 resistors. But we want to totalize. What is the total resistance of all of this? It will certainly be less than all of these together, and even less than the smallest one, right? That's the nature of when you're paralleling components like these resistors. So we will use our trusty reciprocal formula. R total is equal to 1 over the value of R1 plus 1 over the value of R2 plus 1 over the value of R3. What is R1? R1 is 10. What is R2? R2 is 20. What is R3? R3 is 50 ohms. And we just continue the next step, substituting 10, 20, 50 into the formula. Then we go to the next step. We work that out on our calculator. We could punch it in. However, we don't have to do all of these steps. We're just showing it for clarity so that anyone has any difficulty following will see how we get from one step to the next. So 1 over 10 is 0.10. 1 over 20 is 0.05. 1 over 50 is 0.02. So we are continuing to solve. And therefore, when we add 0.10 plus 0.05 plus 0.02, we should get 0.17. And that's the next equation. R is equal to 1 divided by 0.17. We use our calculator and we get R is equal to 5.9 ohms. And that's the answer. Right, so that's it for resistors in series and parallel. Let's come to another component now, inductors. So we would have covered this in the technician class, but we're just reminding ourselves what's an inductor. Well, this is what it looks like. It's a coil, right? And an inductor has inductance and it's measured in henries, right? So L is the symbol, the letter that we use. All right. So similarly to resistors, we can connect multiple of them in parallel or series. So let's deal with the series connected inductors, right? So if you look at the bottom of your screen here, you'll have 3 inductors connected in series here, L1, L2, and L3. We give them labels, right? So when we connect inductors in series like this, is they're similar to resistors. The inductance adds up just the same way if they were resistors, the resistance would have added up by just simply summing them. So that's why we say also that the formula is similar, that L total is equal to L1, the value of, plus L2, the value of, plus L3, and so on. If we had 4 inductors, 5 inductors, we continue adding them up. So this is our trusty diagram showing 3 coils or 3 inductors in series. They add up. And this is an exam question. An inductor in series is the component that should be added to an inductor to increase the inductance. So if you want to increase inductance, you have an inductor or 2, and you want to increase it, you just add another inductor in series. This is an exam question. Similar again to the case for resistors. So let's do a worked example to illustrate where we have 2 inductors in series. What do we get as a total inductance? So let's deal with the question, and this is an actual question in the exam. What is the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor? So let's dissect this question. What are they asking us? What is the inductance? So the answer will be in henries or maybe some millihenry or something like that. They're asking us for what is the inductance. So that will be our answer format, something in terms of henries, right? It's a circuit with 2 components, a 20 millihenry inductor and a 50 millihenry inductor, and it's connected in series. So they've given us, when we dissect this question, they've given us all of the information. We just need to plug that out, plug out the relevant information from the question, and we draw a little diagram here. We show 2 coils or 2 inductors. They're in series, L1 and L2, and the value of L1 is 20 millihenry. I will write that in here. 50 millihenries for L2, I'll write that in here. So we can see the circuit, our schematic diagram, and then we start to solve. So we write the formula down. So the L total is equal to the value of L1, which is inductor 1, plus the value of L2, which is inductor 2. But did they give us L1 and L2? Yes, they did. L1 is 20 millihenries. L2 is 50 millihenries. And we put that into the formula here. So we get the total is equal to 20 plus 50. And add them together, you get 70 millihenries. And that's how we work out for inductors that are connected in series. So you probably guessed we have to now deal with inductors in parallel. So on the right-hand side of your diagram here, we have these inductors or coils L1, L2, L3, and so on. And they're connected in parallel, right? Similar to how we had the resistors connected in parallel. This is what parallel circuitry looks like. Thing is, when we add them up like this, you actually end up with a total that is less or lower inductance, right? So similar to resistors, when you add more inductors, you're not increasing the inductance, the total inductance, you're actually decreasing when you connect them in parallel. If they were in series, yes, you'll be adding up the inductance. So similar to the resistor formula, L is equal to 1 all over 1 over L1 plus 1 over L2 plus 1 over L3 and so on. So very similar to the resistance, instead of R, we have L. So this is the formula. And similarly, if all the inductors are the same value, you have a simplified version of the formula, which is the total inductance L total is equal to L1, any one of the values of the L or the inductor divided by the number of inductors. So if you had 3 inductors, this denominator here will be 3. If you had 2 inductors, it will be 2 and so on. So let's do a worked example of inductors connected in parallel and see how that works out. Right, so let's deal with the question. And again, this is a question in the question pool. This is an exam question, right? We've just worked out how do we get the answer, right? So the question, let's go at it. What is the inductance of 3 10 millihenry inductors connected in parallel? So let's dissect this question. What are they asking us for the two inductance? So if it's the inductance, the answer is going to be in henries of some sort, right? Of what? Well, they're telling us we have 3 inductors and each of them are the same value of 10 millihenry each. So we draw out our little trusty inductor in parallel circuit diagram or schematic here. L1, L2, L3, 3 coils or 3 inductors, they are in parallel. So L1 is 10 millihenry, we could write that down. L2 is 10 millihenries, we could write that down if we wish. And L3 is 10 millihenry. So 10 plus 10 plus 10, or I should say 10 and 10 and 10, all of them are 10. But we cannot just add them at all. Why? They are not in series, they are in parallel. So we have to use the short version of the formula. We could have used the long version, but because they're the same value, remember we dealt with the formula here, L1 of any one of the values of the inductors divided by the number of inductors. So we'll use that short version of the formula. Total of the inductance is equal to the value of one inductor divided by the number of inductors. And this only holds if the inductors have the same value. Otherwise, we'll have to use the longer formula. So it makes life a little simpler for us using the short version of the formula. What is L1? L1 is the value of any of the inductors. Did they give us that? Yes, it's 10 millihenry. All of them are equal. So 10 is the numerator divided by the number of L. The number of L is how many inductors? Well, it's 3 of them. So that's how we get the 3. And if you divide 10 by 3, you get approximately 3.3 millihenries because it's inductance. So that's the worked example. It's an exam question. Again, feel free to write out the question and write out the formula and the solution and see for yourself how you get step by step the correct answer. You can easily learn the answer, but with the 430 odd questions to learn all those answers, sometimes it's better to learn the concept, learn the formula, and work out the answers that you will get, right? Either which way, whichever you're more comfortable with. But at least you've seen how to work the answer out, so you have become familiar with the theory and the formula associated with it. Try your best to learn it. It will be helpful to you as a radio amateur when you're doing calculations and so on, right? Of course, you won't have a formula sheet in the exam, but of course, looking up a formula is something you can always do. But how do you apply the formula? And that's what we are demonstrating here. Right. So the last component that we'll deal with this evening, and we'll just run a few minutes over this evening, folks. So bear with us. Will be capacitors. And you're probably guessing that we'll have to deal with capacitors in series and capacitors in parallel in a circuit. And you'll be quite right. That's exactly what we'll be doing. So we're just reminding ourselves what a capacitor is. We dealt with this in the technician class level ad nauseum. We went through in detail what it is. So there are two things we need to talk about with respect to capacitors, what they are. So this is a capacitor here, right? So remember, it stores electric charge in electric field, right? That's what it does. That's what a capacitor does, opposed to the coil or the inductor that stores it in a magnetic field. And this is what it looks like. These are the symbols and so on. This is just reminding ourselves what a capacitor is. But I want to just spend a moment or two going through the units of nano, micro, pico, and so on, because some of the questions that we will get, they'll mix the units for you. They mix the prefixes and tell you nanofarad and picofarad and what's the total, and you have to convert. So we did this in the technician class, but let's remind ourselves, right? So of course, in terms of the units, right, a farad is a very big number. So we normally talk in terms of microfarad, nanofarads, and picofarads. So if you want, have a look at session number 4 to remind yourselves. We will go into very great detail as to how to convert up and convert down from microfarad to nanofarad to picofarad and so on. We're just repeating some of these slides here. We wouldn't go into detail here other than to refer you to session number 4 in the technician class video. Please have a look at it. We go through this in detail. All right. So we also have an example here, just for your purpose. If we had to convert from nanofarad, from picofarad to nanofarad, this is how you do it here. This is just an example. Also, similarly, if we have to convert from nanofarad to microfarad, this is how we do it here. So sometimes we have to do it in a calculation. And in a couple of the questions that we do have to convert, right? So these are just here for you to look at and refamiliarize yourselves with the units when you're converting from milli, micro, nano, pico, kilo, mega, and all of that, right? Those unit conversions. Right? Right, so let's get to the meat of the matter. So we did talk about capacitors, what they are. And sometimes in a circuit, we will have multiple capacitors in the circuit, one after the next. So when we connect capacitors, similarly to resistors and inductors, we can connect them in parallel or series. So what is this? If you were to guess, well, these look like series connected capacitors, you'll be quite right. So hopefully you're getting the pattern now. Series, one into the next, they flow straight one into the next. They're daisy chained, So capacitor 1, capacitor 2, capacitor 3, and they are series connected. And we need to be able to calculate, if we have the values of these, each one of them, what will be the total capacitance. So we need to know that this is in fact the opposite case to resistors and inductors, right? When you're adding more capacitors in series, it will actually decrease the total capacitance. And this is an exam question, right? So you need to know this, right? Put them in series, it decreases the total capacitance, right? You need to be aware of that. And of course, when we come to parallel, you'll see what pertains. And you probably would have guessed, yes, if you put them in parallel, you're actually summing or adding them together, right? There's a pattern to all of this. In the formulae are very similar to each other, which kind of could help in memorizing, right? So the more you practice it, the more it will become second nature to you. So this is the case here of the total capacitance. If you have multiple capacitors in a circuit, how we calculate it. So we did say it will decrease when you add these up and they're in series, right? This is the formula of how you add them up, right? You have to use this reciprocal formula, 1 over C1 plus 1 over C2 plus 1 over C3 and so on, right? Again, this should become a bit familiar now because we've used this type of formula before, except we're now talking about capacitors, and that's why we're using the letter C. So for capacitors in series, as we add more capacitors into the circuit, the total capacitance actually decreases. That's for it in series. Now, if all of the capacitors are the same value, we could use a short version of the formula. The value of one capacitor over the number of capacitors. If it's 4 capacitors, this denominator will be 4. Okay, so let's do an actual example again, very similar to what we did before. And this is an exam question. What is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? So they happen to give you the values of the 2 capacitors, and they have also given it using the same unit, microfarads. In another question will come up shortly, you'll see how they try to trick us and use different units. All right, so the first thing we do, we draw out our circuit. We see it's two capacitors, capacitor 1, capacitor 2. And when we dissect the question, we see that the capacitors are in series. They are not in parallel. So they've told us series. So we write down or we draw out on our piece of paper series connected capacitors. And then we know we need to use our series connected capacitor formula, right? Which is the reciprocal because it's decreasing. And we write that formula down, right? It's two capacitors, but they are different values. So C is equal to 1 over, or 1 all over 1 over C1. Did they give us C1? Yes, they did. It's 20 microfarad. Plus 1 over C2. Do we have C2? Yes, it is 50 microfarad. So we substitute these two values and we end up 1 all over 1 over 20 plus 1 over 50. That's how we get from this equation to this equation. We substitute the values for C1 and C2. Here we are. C1 is 20, C2 is 50. We get to this next equation now. C is equal to 1 all over 0.05 plus 0.02. We add this up together and we get 0.07. So that's how we end up with C is equal to 1 over 0.07. We use our trusty calculator and we divide 1 over this and you get 14.3 microfarads. You can use the calculator and confirm that is so. And that's the answer to this question. All right, let's do another example of capacitors in series, and this is an exam question also. What is the capacitance of three 100 microfarad capacitors? Sorry for the typo, it's capacitors connected in series, right? We'll correct this for when we submit these slides. All right, so we use our formula. Well, we write out or we draw out the capacitors C1, C2, and C3. They are in series, so we're expecting the total to be lower or less than the value of any one of them, right? We're not expecting a value in excess of this because they are in series. They're not in parallel, in series. And therefore, as we learn the rule for capacitors, as we put them in series, the total of all of them together will be less as we add them together in the circuit. So C is equal to 1 all over 1 over C1 plus 1 over C2 plus 1 over C3, right? C1 happens to be equal to C2, happens to be equal to C3. It's the same value, 100. So that's why the denominator here is 100 for all of them. So when we calculate out, we'll have 1 over 0.01 plus 0.01 plus 0.01, which is 1 over 0.03. Use our trusty calculator, do this division, and we'll get 33.3 microfarad. Now we could have also used this shortcut formula as well, and we encourage you to try that out for yourself using the shorter version of the formula for the case where the values of the capacitors are the same. All right, so just because we did series, we now have to come to the case of the parallel capacitors. So notice in this circuit here, we have three capacitors in parallel, C1, C2, and C3. So in this case, when we put capacitors in parallel, the summation, or you sum the values to get the total capacitance of all of them together. And that's why the formula is the C total is equal to C1 plus C2 plus C3. Straight sum, right? And adding more capacitors in parallel will increase the total capacitors in parallel. Notice they are connected in parallel, not series. And an exam question is also a capacitor in parallel is the component that should be added to a capacitor to increase the capacitance. So if you have one capacitor or two capacitors and you want to increase the capacitance, you can add another capacitor in parallel. So let's end by doing a worked example for capacitors connected in parallel. And notice this is the case where they try to mix us up and use different units, right? So let's go with the question. What is the equivalent capacitance of two 5.0 nanofarad capacitors and one 750 picofarad capacitor connected in parallel? Wow. Let's dissect this question a little bit, right? So there are actually three capacitors in this circuit. Two of them are 5 nanofarad capacitors, right? And one of them is a 750 picofarad. So if we were to label, so first of all, we draw our three capacitors in parallel, C1, C2, and C3. C1 is equal to 5 nanofarads. C2 is equal to 5 nanofarads as well. We have two 5 nanofarad capacitors, that's C1 and C2. But C3 is a 750 picofarad capacitor. So 5 nanofarad, 5 nanofarad, 750 picofarad. And we know we need to add up these values and we'll get the total, but we can't just add it. We have to do a little conversion first of all, right? But let's write the formula. The total capacitance of C total is equal to the value of C1 plus C2 plus C3. But we need to convert all values, let's say, to one equivalent first, nanofarads, right? So we know that C1 and C2 is 5 nanofarad, but C3 is 750 picofarad. So we have to convert it to nanofarad. And as we have learned in the technician class, and we have just done a snapshot here, to go from picofarad to nanofarad, we have to divide by 1,000. So we have 750 picofarads divided by 1,000 to give us nanofarads, which is 0.75 nanofarads. So now we could add that 0.75 to the other value of 5 nanofarads. So 5 for the first C1, 5 for the C2, and C3 is 0.75 nanofarads, right? We have to have nanofarads. We could not have left it as picofarads. We will not been able to, it's not apples and apples, right? So we would have had to convert it to all nanofarads. And when we add them up, we get 10.750 nanofarads. So folks, that's the theory for this evening. We do have our question pool review that we will do quickly for all of the questions that we just covered in the sessions, right? So let's switch across to the question pool. All right. First question up. What dB change represents a factor of 2 increase or decrease in power? So we worked this out for both the increase case and the decrease case. And in the case of increase, it was 3 dB. And in the case of decrease, it was negative or minus 3 dB. So approximately 3 dB is the answer if you have a factor of an increase of twice times or half times, right? All right, next question in the question pool. What percentage of power loss is equivalent to a loss of 1 dB? So again, we worked this out and showed that the power loss is 20.6%, 20.6%. Next question in the question pool. What is the approximate total resistance of a 100 and 200 ohm resistor in parallel? So we did the schematic diagram. We used our trusty formula for resistance to show in parallel it will be less. So we used that formula, and when we worked it out, we got 67 ohms. All right, next question in the question pool. What is the total resistance of a 10, a 20, and a 50 ohm resistor connected in parallel? Let's dissect this question. What are they asking us? Total resistance of what? Well, it's 3 resistors, 10, 20, and 50 ohms, connected in what? Is it series or is it parallel? So we'll know which formula to write down or which schematic diagram to use. It's parallel. So when we use that formula, we get the answer 5.9 ohms. Next question in the question pool. Which of the following components should be added to an inductor to increase the inductance? So we did say that if you have an inductor and you want to increase it, you have to add another one in series. Again, inductors operate the same way like resistors. If you want to increase it, you add one more in series. If you put it in parallel, you actually be reducing. All righty. Next question in the question pool. What is the inductance of a circuit with a 20 millihenry inductor connected in series with a 50 millihenry inductor? So let's dissect this question. What are they asking us? They're asking us for the total inductance of 2 inductors. First one is 20 millihenries and the other one is 50 millihenries. So they are in series. So therefore we have to add them up. So use that summation formula and we get 70 or 70 millihenries. Next question in the question pool. What is the inductance of 3 10 millihenry inductors connected in parallel? Right. So we did this also as a worked example. And we saw it's 3 equivalent value inductors and they are in parallel. So we use the appropriate formula, which is the reciprocal formula, and we end up with 3.3 millihenries as the answer. Next question in the question pool. What or which of the following components should be added to a capacitor to increase the capacitance? So let's dissect this question. What are they asking us? So you have a capacitor in a circuit, but you want to increase the capacitance of that circuit. What do you do to increase it? Well, the answer is you have to put a capacitor, but is it going to be parallel or in series? Remember, if it's in series, it will reduce. But if you put another capacitor in parallel, it will increase the value of the capacitance. And that's the answer. A capacitor in parallel is the answer. What is the capacitance of a 20 microfarad capacitor connected in series with a 50 microfarad capacitor? So let's dissect this question also. They're asking you for what is the capacitance. So it has to be in something farads, right? It's two capacitors. It's 20 microfarad is the first one and 50 microfarad is the other one. But how are they connected? Are they connected in parallel where they'll be simply added up? No, they're connected in series. So you have to use the reciprocal formula and it will be less. So the answer is 14.3 microfarad as we calculated in the worked example. All right, next question in the question pool. What is the capacitance of three 100 microfarad capacitors connected in series? Dissecting this question, they're asking us for capacitance, so that we know the answer is going to be in farads. Of what? It's three capacitors and their equivalent value, 100 microfarad. But are they connected in parallel where we'll simply add them up and it'll be larger than any one of them? No, they're in series, so we know we have to use the reciprocal formula and the total will be less than any one of them, right? So we use our trusty formula and we end up with 33.3 microfarad as per the worked example. All right, so last question in the question pool to match the theory that we covered. Again, students, we are covering every single question in the question pool during the course. So by the time you're finished, there will not be a single question that you have not looked at in some level of detail, and you should be quite familiar with each of the questions. So there should be no surprises in the exam. You should be relatively comfortable to know that you would have no unseen questions. You would have dealt with all of them, and it's just a matter of familiarizing yourself and going after it, right? So last question, what is the equivalent capacitance of two 5.0 nanofarad capacitors and one 750 picofarad capacitor connected in parallel? Let's dissect this question. What are they asking us? It's capacitors. How are they connected? They're connected in parallel, so we can draw them out. So we already know that we have to use the reciprocal, it's connected in parallel. So we know we have to use the summation formula, right? And the total will be more than all of each one of these, right? So we use the summation formula. But how many capacitors do we have? Is it two capacitors? No, it's three. Two of them are 5 nanofarads and one of them is 750 picofarad, but we have to do a conversion because we cannot add nanofarads directly to picofarads. So we have to convert the picofarads first to nanofarads, and then we can do a straight summation and we'll get the total of 10.75 nanofarads. So let's return to our slide deck. All right, so for those who might be following in the text, we are in fact on between pages 11 and 15, all right? So, right, there we go. All right, so folks, we do have a couple of slides with some announcements coming up towards the end of the slide deck. So folks, any questions, feel free to send me an email at this address or via WhatsApp at this mobile number. Right. So we have a WhatsApp channel for persons who would like to get updates via WhatsApp, including the updates on the links for the course. Some people will prefer WhatsApp. So if you would like that method, you can take a note of, or when you get the slide deck, you will have this link available to you. You can click on this and add this channel on your WhatsApp, and we'll be sending information on that channel, including information about the course itself and so on. So apart from the email, this will be another way that you'll get information. Some persons, it may be more convenient to receive that information via WhatsApp, right? So feel free to join this channel, all participants. You will have this in the slide deck. It's a little bit lengthy. All right, so you can take a snapshot or you can write it down if you wish, or you can get the slides, let's say by tomorrow, and you can click on the link. All right. Right. So For React members in the class, this slide is for you. So we are offering a Microsoft 365 subscription for members of React in Trinidad and Tobago. This is a link to apply for your subscription. So it has been in circulation via the council for a few days, but just in case you have not seen it, please use this link should you wish to avail yourself of that subscription to Microsoft 365. All right. Again, you'll get that in the slide deck, or you can take a screenshot, or you can write it down if you wish. All right, folks. Our next session, God's willing, will be next Friday, the 17th of November. Usual start time, 8:30 p.m. Thank you very much, everyone. We want to wish tomorrow in Trinidad, well, Sunday is Diwali, and public holiday on Monday as well. So we certainly wish everyone a happy Diwali. Be safe, take good care, and hopefully see you in next week's session. Everyone, have a good night.